Welcome to the lecture of Introduction of Renewable Energy. In today's lecture, we will discuss about the energy extraction from the tidal power and ocean waves. The rise and fall of the sea represent a vast and relentless nature of phenomena. The tidal power is the result of the interaction of the gravitational pull of the moon and to a lesser extent the sun on the sea. The gravitational force combined with the rotation of the Earth produces at any particular point on the globe a twice daily rise and fall in sea level. This being modified in height by the gravitational pull of the Sun and by the topography of land masses and ocean beds. There are two types of process that exist between Earth and Moon. That is, a rotational effect and a gravitational effect. The first process, the rotational effect, is the result of the fact that the Earth and the Moon rotate around each other, some like a dumbbell being twirled. This rotation gives rise to an outward force or called centrifugal force, which act on the water in the sea. However, this giant dumbbell does not rotate around the halfway point between the Earth and Moon. Since the Earth is much larger than the Moon, their common center of rotation is close to the Earth. In fact, it is just below its surface. The mutual rotation around this point produces a relatively large outward centrifugal force, acting on the sea on the side of the Earth furthest from the Moon, bunching them into bulbs. There is also a much smaller centrifugal force directed toward the Moon that act on the sea facing the Moon. The second process, the gravitational effect, is more familiar and relates to the gravitational pull of the Moon, which draw the sea on the side of the Earth nearest to the Moon into a bulge toward the Moon, whilst the sea furthest from the Moon, being further away, experience a reduced lunar pull toward the Moon. There is thus, to summarize, a small centrifugal force and an increased lunar pull acting on the sea facing the Moon, and in a larger centrifugal force and a decreased lunar pull acting on the sea on the other side of the Earth. The end result on the basis of this analysis is essentially a rough symmetry of forces, small and large, on each side of the Earth, producing tidal bulge of roughly the same size on each side of the Earth. In practice, the bulge may differ significantly due to the tilt of the Earth axis in relation to the orbit of the Moon and to local topographic effect. If Earth were not rotating and the Moon was fixed, then the bulge would remain in the same location on Earth. Relative to the Moon, the bulge stays fixed. Along the line connecting Earth and the Moon, but Earth rotates approximately every 24 hours. In 6 hours, the near and far location of Earth move to where the low tides are occurring, and a 6 hours later, those locations are back to the high tide position. Since the Moon also orbits Earth approximately every 28 hours and in the same direction as Earth rotates, the time between high and low tides is actually about 12.5 hours. When the Sun and Moon pulls together, whether both pulling on the same side of the Earth or each on opposite sides, the result is the very high spring tides. When the Sun and Moon are at 90 degrees to each other, the result is the lower neap tides. The period between neap and spring tides is approximately 7 days. The ratio between the height of the maximum spring and minimum neap tides can be more than 2 to 1. The basic principle or the basic physics and engineering of tidal barrage power generators are relatively straightforward. Tidal barrages built across suitable creeks or bay are designed to extract energy from the rise and fall of the tides. Using turbines located in water passage in the barrage, the potential energy due to the difference in water level across the barrage is converted into kinetic energy in the form of fast moving water which passes through the turbine. The spinning turbines then drive generators to produce electricity. The average power output from a tidal barrage is roughly proportional to the square of the tidal range. For average power potential calculation, consider a rectangular basin with a constant surface area A behind a barrage and a high to low tide range H. In conventional ebb generation, when the tides come in, it is fairly allowed to flow into the basin. But when the tide goes out, the water in the basin is held there at the high tide level. When the sea has retreated to its low tide level, the surface of the water behind the barrage will be at a height h above the sea level. If the tidal period is T, then the average potential power that could be extracted become density times area, surface area, times height or range into gravity divided by 2 times of time period. Clearly, even small difference in tidal range can make a significant difference to the viability and economics of a barrage. A mean tide range of at least 5 meters is usually considered to be the minimum for viable power generation depending on the economic criteria used. The input energy source for a barrage, the rise and fall of the tides following a roughly sinusoidal pattern as shown in this diagram. The tides have a 12.4-hour cycle with the actual tidal range varying from side to side as a result of complex resonance and funneling effect. Energy can be generated from a barrage in three main ways. The most commonly used method is ebb generation. Here, the incoming tide is allowed to pass through the barrage gate. The water is trapped behind the barrage at high tide level by closing the gate. The head of the water then passes back through the turbine on the outgoing ebb tide in order to generate energy. Alternatively, flood generation uses the incoming tide to generate electricity as it passes through the turbines mounted in the barrage. In each case, two bursts of energy are produced in every 24-hour period. During the flood tide, the gates and turbines are kept closed until a substantial hydrostatic head has developed across the barrage. Once the sufficient hydrostatic head is achieved, the turbine gates are opened, allowing the water to flow through them into the basin. Flood generation is a less favorable method of generating electricity due to the effect on shipping and environment. These effects on shipping and the environment are caused by the average decrease in sea level within the basin. Flood pumping is another option for electricity generation. Here, the turbine generators are run in reverse and act as a motor pump sets powered by electricity from the grid. Additional water is pumped behind the barrage into the basin at around high tide, where there is a low head difference across the barrage. This provides extra water for the subsequent ebb generation phase when there is high head difference. This is in effect a way to store excess off-peak power from the grid but with the net energy gain. Two-way operation on the ebb and the flood is also possible as illustrated in the diagram. This method of operation utilizes both flood and ebb phase of the tide to generate electricity. The channel gates and turbines are kept closed until near the end of the flood cycle. After this point, the water is allowed to flow through the turbine, generating electricity. When the minimum hydrostatic head for generating electricity is reached, the gates are then opened. At high tide, the gates are closed and the water is trapped behind the barrage until a sufficient hydrostatic head is reached once again. Water is then allowed to flow through the turbine to generate in the ebb mode. Two-way generation has the advantage of a reduced period of non-generation and a reduction in the cost of generator due to the lower peak power. The electricity produced by barrage must usually be integrated with the electricity produced by the other power plants that feed into the national grid power transmission network. The key problem in feeding power from a tidal barrage into national grid network is that the conventional ebb or flood generation schemes, the tide energy inputs come in relatively short bursts at approximately 12-hour interval. Typically, power can be produced for 5 to 6 hours during spring tides and 3 hours during neap tides within a tidal cycle lasting 12 hours as shown in the diagram. Clearly, such availability of power from a barrage will not always match the pattern of demand for power on the grid. With large well-developed grid with a large load and many other types of power plant connected into it, this problem might not be too severe, depending on the size of the barrage and the flexibility of the output. The availability of large amount of electricity storage capacity could also help. Two-way generation on the incoming flood as well as the ebb might offer some advantage since that would give 4 bursts of power for each 24-hour cycle. But more complex turbine required adds to the cost. There is also the option of using modified turbines as pumps running on the grid power. Example, during off-peak period to pump extra water behind a barrage during the flood phase. Typically between 5% and 50% extra output can be gained. However, the overall economic advantages of pumping may be fairly small, and they depend crucially on tidal timing, which will not necessarily coincide with the off-peak grid power availability. The basic technology for power production is well developed, having much in common with conventional low-head hydro systems. A number of different turbine configurations are possible. At L.A. Ran's tidal barrage, a so-called bulb system is used, with the turbine generator sealed in a bulb-shaped enclosure mounted in the flow. As the water has to flow around the large bulb, access for maintenance to the generator involves cutting off the flow of water. These problems are reduced in the rim generator, with the generator mounted radially around the rim and only the runner in the flow. Although it is more efficient than the bulb design because the water flow is not so constrained, this design introduces extra problem with the sealing between the runner blade and the radial generator. Alternatively, there is the tubular turbine configuration, with the runner set an angle so that a long shaft can take rotational energy out to an external generator. This design also avoid constructing the flow of water and since the generator is not in a confined space, there is room for a gearbox, which can allow for sufficient or efficient matching to the higher speed generators usually used with hydro plants. The largest turbine of this type is installed having the capacity of 25 MW. However, there have been vibration problems in the long drive shaft and so far bulb turbines have proved to be the most popular with the barrage designer. The rotational speed of the turbines in tidal barrage tend to be lower than those for turbines in hydro plants, that is about 50 to 100 rpm, whereas in hydro plants it's 200 to 450 rpm and therefore wear is also reduced. Since large volume of water have to pass through the barrage in a relatively short time, large number of turbines are required in a large-scale barrage. In a simple ebb or flood generation, this large installed capacity is used only for a relatively short period in each tidal cycle, producing a large but short burst of power, which may not match the demand of electricity. However, using reversible pitch turbine, it is possible to operate on both the ebb and the flood in a two-way operation. Reversible turbines are more complex and costly than standard turbines, and although the output will be more evenly distributed over time, there will be a net decrease in electricity output for each phase compared with a simple ebb generation scheme. This is because in order to be ready for the next cycle, neither the ebb nor the flow generation phases can be taken to completion. It is necessary to open the gate and reduce water levels ready for the next flood cycle and vice versa for ebb generation. The total power in the tides globally is very large, of the order of 3000 gigawatt. In practice, since there are geographical access and location constraints on siting barrage or other means of obtaining tidal energy, and they also have to be reasonably near to major lines of national grid. The realistically available resource is much smaller. Some estimation says that the realistic recoverable resource is about 100 gigawatt. Although that is under 12% of the existing global hydroelectricity capacity, it still represents a significant resource. List of few tidal power plants are shown here. The Lorentz tidal power plant was constructed in 1967 in France and has the capacity of about 240 megawatt. There are some other relatively small tidal power plants in China of about 3.2 to 5 megawatt. Note that the capacity of power plant is large with respect to small head height. In this diagram, you can observe the design of Lorentz tidal power plant. The operational pattern initially adopted at Lorentz was to optimize the uniformity of the power output by using a combination of two-way generation and incorporating an element of pumping storage. For spring tides, a two-way generation was favored. For neap tides and some intermediate tides, direct pumping from sea to basin was sometimes carried out to supplement generation on the ebb. The 740-meter long Rance barrage was constructed between 1961 and 1967. It has the road crossing and ship lock and was designed for maximum operational flexibility. It contains 24 reversible two-way turbines, each of 10 megawatt capacity, operating in a tidal range of up to 12 meters, with a typical head of approximately 5 meters. although some mechanical problems were encountered in 1975, which subsequently led to two-way operation mostly being avoided. Overall, the barrage has been very successful. Typically, the plant has been functional and available for use more than 90% of the time, and net output has been approximately 480 gigawatt hour per year, with in some years significant energy gain from pumping. The construction of the barrage involved building two temporary coffer dams, with the water then being pumped out of the space in between to allow work to be carried out in dry conditions. River water was allowed to pass via gates, but the reduced ebb and flow resulted in effective stagnation of the bay and the subsequent partial collapse of the ecosystem within it. Since construction, exchange of water between the open sea and the creek has restored the ecosystem. Instead of using costly and invasive barrage in creek to create potential energy head with trapped water, it is possible to harness the energy in the horizontal movement of the tides, that is, kinetic energy of the tidal ebbs and flows. In open sea, the speed of the ebb and flow of the tides is relatively low, but restriction caused by island, channels, and headland can significantly accelerate the stream. The enhanced velocity of the tidal stream in these locations concentrates the energy and provides the most cost-effective sites to harness this resource. There are many technologies designed for this, but turbines closely resemble underwater wind turbines have proven most of the popular with the developers. The basic physics of power extraction from the tidal stream is similar to that of wind turbine. That is half time water density multiplied by rotor swept area and the cube of water stream velocity. Typical horizontal axis propeller design is shown in this diagram. With this structure, turbines can be raised out of the water for easy access. The most obvious difference between the wind turbine and tidal devices is the construction of energy is the concentration of energy due to water being much denser than water air. Less obvious is the resulting load fluctuation on the drivetrain and blade from the turbulence generated from the tidal flows interacting with the seabed and other topographical features. Vertical axis propeller type turbine can also be installed to extract the energy from the tidal stream. An EU-funded study has been made of the potential for tidal current generation in the Straits of Messina between Sicily and mainland Italy. This involves installing 100 vertical axis turbines on the seabed at a depth of 100 meters. The concept of vertical axis tidal stream turbine is same as vertical axis wind turbine. Stingray is an oscillating hydrofoil that changes the angle of attack toward the tidal current and can be viewed in the figure shown. This results in a lift force that makes the hydrofoil move in a periodic pumping motion. This non-linear motion, however, with the periodic loss of momentum, is resulting in a very large degree of mechanical complexity. A 150 kilowatt prototype was tested at sea in 2002 and again in 2003. However, it proved to be very insufficient and was subsequently abandoned. It seems the energy conversion efficiency as was low, around 9.5%, due to part to the relatively slow oscillation rate. But with two sets of hydrofoils on a seesaw arrangement oscillating much more rapidly. Given the relatively shallow depth of most tidal channels, hydroplanes type design are claimed to have an advantage over propeller-like design in that they can operate in shallower water, with the blade able to traverse a large cross-section area of the tidal flow than the circular area defined by the rotating blades of the propeller-like devices. The possibility of extracting energy from ocean waves have attracted people for centuries. The modern wave energy conversion schemes have few environmental drawbacks, and the prospects are promising that some of them may make a significant energy contribution. The total wave energy resource is large. However, estimates of its magnitude vary widely as the oceans have not been fully monitored over a long enough time period to establish a reasonable value. The World Energy Council has estimated the available worldwide resources to be 2000 terawatt-hour per year. If all potential improvement to existing devices are realized. The wave energy potential, for example, in the EU has been estimated conservatively as 120 to 190 terawatt-hour per year at offshore and 34 to 46 terawatt-hour per year near the shore. Here the offshore means deep into the sea. A rough estimation of technical potential of few countries is listed here. The Denmark has about 2 to 3 terawatt-hour per year of wave energy potential near shore and about 5 to 8 at offshore. Similarly, UK has a high technical potential of wave power. In Europe, near shore, UK can produce about 14 to 21 terawatt-hour per year and at shore 43 to 64 terawatt-hour per year. An overview of worldwide wave power density in kilowatt per meter in peak is illustrated in this diagram. It can be observed that there is substantial wave energy potential all around, though the technology to harness the wave power is not yet mature. Over the years 2001 to 2017, several countries increased their investment in wave energy technology, both from commercial investors and from the government. Ocean waves are generated by wind passing over long stretches of water known as patches. The precise mechanism involved in the interaction between the wind and the surface of the sea are complex and not yet completely understood, but three main forces appear to be involved. Initially, flowing over the sea exert are tangential stresses on the water surface, resulting in the formation and growth of waves. Turbulent air flows close to the water surface creates rapid varying shear stress and pressure fluctuation, where these oscillations are in phase with existing waves, further wave development occur. And finally, when waves have reached a certain size, the wind can exert a stronger force on the upwind phase of the wave, causing additional wave growth. Because the wind is originally derived from solar energy, we may consider the energy in ocean wave to be a stored moderately high density form of solar energy. Solar power levels, which are typically of the order of 100 watt per meter square, can be eventually transformed into waves with power level of over 100 kilowatt per meter of crystal length. Note that these power levels are reported in different units, that is, per square meter and per meter of crystal length. This is because of the nature of wave, making it impossible to refer to power per unit area. We have to consider that the wave action takes place throughout the depth of water, and so we consider the power passing through a 1 meter wide slice of water. We cannot therefore directly compare solar and wave power densities, but can state that the solar to wind to wave sequence gradually concentrates the power density. Let's start by looking at an idealized wave as shown in this figure. This simple regular waves can be characterized by its wavelength lambda, that is the distance between successive peak or troughs of the wave. Second, its height, referred to capital H, the difference in height between peaks and troughs. And last, its period, the time in seconds taken for successive peak to pass a given fixed point. Waves of greater height contains more energy per meter of crest length than small waves. Waves located within or close to the area where they are generated are sometimes referred to as wind C. When wind changes in strength and direction, the resulting wave pattern can become quite complex. Waves can travel out of these areas with minimum loss of energy to produce swell waves at great distance from their area of origin. As the wave travels, there is a systematic tendency for periods and wavelength to increase, and so swell C are typically made up of relatively long period waves. The height and steepness of the waves generated by any wind field depends upon three factors, that is, the wind speed, its duration, and the fetch, that is, the distance over which wind energy is transferred into the ocean to form wave. When the steady wind has blown for sufficient time over a long enough fetch, the waves are referred to as constituting a full developed area. The shape of typical wave is described as sinusoidal, that is, it has the form of mathematical sine function. The difference in height between peak and trough is known as the height, and the distance between successive peaks of the wave is known as the wavelength. Suppose that the peaks and trough of the wave move across the surface of the sea with the velocity v. The time in seconds taken for successive peak to pass a given fixed point is known as the period, designated as capital T. The frequency f of the wave describes the number of peak-to-peak oscillation of the wave surface per second as seen by a fixed observer and is the reciprocal of the period. That is, frequency is equal to 1 by time period. If a wave is traveling at velocity v past a given fixed point, it will travel a distance equal to the wavelength in a time equal to the wave period t. So the velocity v is equal to the wavelength divided by the period t. The power p of an idealized ocean wave is approximately equal to the square of the height h in meter multiplied by the wave period t in second. There are differences between waves in deep and shallow water. In terms of wave propagation, water is considered to be deep when the water depth is greater than about half of the wavelength. The velocity of a deep water ocean wave can be shown to proportional to the period as velocity is equal to gravity times time period divided by 2 pi. This leads to the successful approximation that the velocity in meter per second is about 1.5 times the wave period in seconds. An interesting consequences of this result is that in the deep ocean, the long waves travel faster than the shorter waves. This is referred to as dispersion, a unique feature of deep water waves which can lead to dangerous and hard to predict combination of wave crest. Long waves can catch up with preceding shorter wave, creating large combined waves where they meet. If both the above relationship hold, we can find the deep water wavelength for any given period as lambda is equal to gravitational constant times time period square divided by 2 pi. In the intermediate depth waves, as the water becomes shallower, the property of the waves become increasingly dominated by water depth. When waves reach shallow water, their properties are completely governed by the water depth. But in intermediate depth, that is between depth is equal to lambda divided by 2 and depth is equal to lambda divided by 4, the properties of the waves will be influenced by both the water depth d and the wave period t. As the wave approaches the shore, the seabed starts to have an effect on their velocity, and it can be shown that if the water depth d is less than a quarter of the wavelength, the velocity is given by v is equal to square root gravitational constant times d. D is the depth. In other words, the velocity under these conditions is equal to the roughly 3 times the square root of the water depth, and it no longer depends on the wave period. The surface profile of the ocean is the obvious evidence for the existence of the waves, but we also need to understand the subsurface nature of the waves if we are to design schemes to capture energy from them. As shown in the figure, waves are composed of orbiting particles of water. Near the surface, these orbits are same size as the wavelength, but the orbit decreases in size as we go deeper below the surface. The size of the orbit decreases exponentially with the depth. 95% of the wave energy is contained in the layer between the surface and the depth equal to a quarter of the wavelength. There are a few areas in the world where the shoreline is formed by a steep cliff that drop into reasonably deep water. These are the most suitable for shore-mounted wave energy converters because the incident waves have a high power density. But for most coastlines around the world, the near-shore water is quite shallow. Due to the frictional coupling between the water particles at the greatest depth with the seabed, deep water waves gradually give up their energy as they move into shallower water and eventually run up the shore to the beach. This power loss obviously reduces the total wave energy resources. Typically, waves with the power density of 50 kilowatt per meter in deep water might contain 20 kilowatt per meter or less when they are closer to shore in shallower water. To capture energy from sea waves, it's necessary to intercept the wave with a structure that will react in an appropriate manner to forces applied to it by the waves. In a shore-mounted device, the structure is firmly fixed to the seabed and the waves make water move in a useful way. For other types of device, some part of the structure may be fixed, may be fixed, perhaps anchored to the seabed, but another part may be a floating that move in response to the wave by pulling against the anchor. In this case, the relative motion between the anchor and the float provides the opportunity to extract energy. Very loosely chained floating structure can also be employed. but a stable frame for reference must still be established so that the active part of the device move relative to the main structure. This can be achieved by taking advantage of inertia or by making the main structure large enough to span several waves crust, hence remaining reasonably stable in most sea states. A body in the sea subject to waves can respond to six types of movement. These are swinging, roll, and yaw, not generally harnessed in wave energy conversion technology. Three more harnessed to varying degrees in most wave energy converters are pitch, which causes waves in which waves cause the device or part of it to rotate about its axis, heave, in which waves cause the device to rise and fall vertically, though these devices have too high R natural frequency to be practically effective, and the surge, in which waves cause the device to move horizontally backward and forward. Theoretically, surging motions are twice as energetic as heaving ones, making it preferable to harness the component of the waves. Economics demands that a device should survive at sea for at least 5 years. During that time, some of its components will have to execute 15 to 30 million cycles, placing severe constraints on material selection and strain level. A structure designed to operate at a particular wave power density will also have to be endure storms with power density 10 to 30 times higher than the operating value. The physical size of the structure of a wave energy converter is the critical factor in determining its performance. The appropriate size can be estimated by considering the volume of water involved in the upper particle orbit in a wave. In most circumstances, a wave energy converter will have to have a swept volume similar to this volume of water in order to capture all the energy contained in the wave. The precise physical size and shape of each device will be governed by its modes of operation, but as a rough guide, the swept volume must be of the order of several ton of cubical meters per meter of device weight. There are many different configurations of wave energy converters, and the number of ways of classifying them have been proposed as shown in this diagram. One approach is to classify by mode of operation. Another approach is to consider the device location. Here the three general classifications are: fixed to seabed, generally in the shallower water; second is tethering in intermediate depth; and the third is floating offshore in deep water. Alternatively, the geometry and the orientation of the wave energy converters may be used. Here the options are terminators, attenuators, and point observer. Illustration of classification by location is shown in this diagram. Wave energy conversion devices are classified by their location: as shore, that is on land, such as tape channel, that is shown over here; a near shore, that is in the relatively shallow water, which is this one, and depth approximate to the wavelength; or offshore, that is in deep water where the depth much greater than wavelength. Terminated devices have their principal axis parallel or almost parallel, since a slight angle helps to increase the stability of the whole body to the incident wave front, and they physically intercept the waves, as shown over here. Depending on the depth, a 300-meter long device in a wave climate of 60 kilowatt per meter, thus intercept up to 18,000 kilowatt energy. Typically, one third of this might be converted into electricity. Attenuators have their principal axis perpendicular to the wave front, so that wave energy is gradually drawn in toward the device as the wave move along it, such as shown over here. A leading buoy and anchor permit the device to swing around and orient to the principal wave direction. An array of terminators or attenuators will require sufficient spacing between individual devices to allow them to swing around on their moorings without fooling their neighbors. A point observer must have small dimensions relative to the incident wavelength and work by drawing wave energy from the water beyond their physical dimension. Typically, being sensitive to waves from all directions, they do not require freedom to orientate to the incoming waves, and so can usually be tightly anchored. In principle, they could be extremely slim vertical cylinders which execute large vertical excursions in response to incident wave. But in practice, the hardware involved tend to mean that they are few meters in diameter and absorb energy from twice their own width. The maximum power absorbed by a perfect point observer is determined by the heaving or surging mode. The principle of wave capture is simple, as observed in many shoreline lagoons and swimming pools. Waves rise up a channeled sea wall, and overspilling water is impounded in a reservoir above the mean sea level. Controlled outlet water returns to the sea through a conventional low-head hydroelectric turbine generators. Figure shown here is a schematic diagram of the 350 kilowatt tap change system demonstrated in Norway in 1985 and since replicated at a few sites worldwide. The, the incoming the incoming waves funnel up a narrowing channel whose concrete wall reached up to 2 to 3 meters above sea mean level. The peaks of these waves increases in height above the trough as the wave progress along the tapered channel, so water spills over into the reservoir as the waves arrives at the wall. Larger waves may overtop the wall directly. The site was chosen carefully to incorporate natural formation with the wall and basin. Sites for wave capture system must possess the features such as persistent wave with large average wave energy, deep water close to shore so the power of oncoming waves is not unduly dissipated, dissipated, a small tidal energy that has less than 1 meter, natural feature benefiting the wave channel and reservoirs. Robust construction of the channel and walls against violent storm since storm's waves are also channeled and enhanced in height toward the elevated basin. The capture length of the tap churn device may be defined as the ratio of average output turbine power to the average power per unit width of the waves entering the lower end of the channel. This device was developed in the Denmark, which has the coastline on the North Sea that has a less intensive wave regime than the Atlantic Ocean. This is called the Wave Dragon floating overtopping terminators. It uses the overtopping method of the early tap chain but with the whole structure floating at the sea. Overtopping waves spill over into a reservoir from which water flows out through turbine generators. Low-head Kaplan turbines have been used for prototype. Waves are reflected and concentrated into the overtopping region but by concave shaped wings that are all part of the floating structure. These also give the structure greater stability, which is important in storm. After the successful prototype development of Denmark, a 7 megawatt capacity device is due to operate off the west coast of Wales. The aperture of the reflecting wings is 300 meters for this commercial scale machine. The height of the top of the reservoir is designed to capture to catch overtopping from average waves so as to optimize generation through the year. The extended structure improves stability in rough sea and the limited depth of the floating structure and limited height of the reservoir allow the energy of large storm waves to pass underneath and over the structure. Waves passes onto a partially submerged cavity open under the water so that the water column oscillates up and down in the cavity. Such a structure is called oscillating water column terminators, as shown in this diagram. This induces an oscillatory motion in the air above the column, which may be connected to the atmospheric through an air turbine connected to an electricity generator. The turbine usually used is a well turbine, which once started continue to turn in the same direction whichever the direction of the airflow. Therefore, generation continue without a break but at varying power amplitude. An advantage of using an oscillatory water column for power extraction is that the airspeed is increased by smooth reduction in the cross-section area of the channel approaching the turbine. This couples the slow motion of the waves to the fast rotation of the turbine without mechanical gearing. Another advantage is that the electrical generator is shifted significantly from the column of saline water. The structure shape and size determines its frequency response, with each form and size of cavity responding best to the waves of a particular frequency. It is essential that the characteristics of the turbine generator are matched to the wave movement. Floating wave energy attenuators floats on or near the sea surface and respond to the shape of the incident waves. They are anchored to the seabed so they align themselves to the average wave energy flux. The oncoming wave power is absorbed progressively by the device and so lessen attenuates as the wave pass by. Such devices have a length comparable to the sea wavelength and a relatively small width. The Pilamis machine have several tubular semi-submerged modules connected by coupling able to move with damping and heave that is vertically and sway that is horizontally in a plane perpendicular to the oncoming wave pattern. The tunable two-dimensional coupling allows the anchor device to have a large capture width, in effect as wave power is absorbed into the devices. Additional wave power is drawn in from adjacent region, and so the capture width is significantly greater than the device head-on width. The wave-induced motion of the coupling is resisted by tunable hydraulic piston, which pump high-pressure oil through hydraulic motors via smoothing accumulators. These hydraulic motors drive electrical generators at each coupling. so producing electricity transmitted by undersea cable to shore. Several devices can be arranged in an array or farm, each with electrical connection to a hub from which power is transmitted to shore via an undersea cable. The 750 kilowatt capacity prototype of 150-meter long in 4 modules and each 3.5 meter in diameter was installed in 2004 offshore of the main island of Orkney, northern Scotland, as the world's first offshore wave power generator connected to a utility grid. The electricity generator immediately by wave power devices, that is without some form of averaging or storage as in overtopping device, varies in amplitude with time. Such variability is similar and perhaps greater than the variability of individual wind turbines. In both cases, averaging the output of multiple machines in array considerably decreases the variability of the combined output. Another device to convert wave energy is called pendular device. It consists of a rectangular box which is open to the sea to one end. The pendulum flap is hinged over this opening so that the action of waves causes it to swing back and forth. This motion is then used to power a hydraulic pump and generator. Worldwide, only small devices have been deployed. Ocean contains considerable mechanical power which can be harnessed especially in those locations where the resources is large and relatively near to the shore for long period. In this lecture we have discussed about the technologies that can be applied to extract ocean power. Today lectures end here. Thank you for listening.